Our goal for this week is to bring in a few techniques from functional programming to help us organize our code better and reduce redundancy. Now, by the end of this set of material, we'll notice that the techniques we've brought in are useful for a lot of other reasons as well. But for now, we're going to push forward with that goal of decoupling behaviors in our program to keep things organized and to avoid having to duplicate code. One of the main tenets of functional programming is the ability to treat functions as data, just like anything else. And we're going to see C++ supports that. We have the ability to make variables that refer to functions. And it's true that since the beginning of 1.11, when functions were introduced, there was this sense of separation between data, so it's what you put in a variable, and functions. They have some similarities. I mean, functions and variables both have names, but there was something special about functions. And I should add, there are ways of treating functions as data to a certain extent in C as well, not as much of an extent as we can do in C++. We just introduced them in 1.11 because people wouldn't have had the patience for that in a course like 1.11. And so it turns out that we can treat functions completely as data in C++. We'll see an introduction to that today, but I should add that over the course of this semester, we've already had hints of that. We've already begun to blur the lines between behavior and data. For example, we've been working with classes, and we know that an object of a class type, a smart object, is some kind of a mixture of just data and functionality and behavior. So it shouldn't surprise us really that much that we can pass things around the program that might not turn out just to be an int or a float, but turn out to be functions that we can then call. And in a more technical sense, it turns out that the operation of calling a function, so that is to say using the round brackets, is actually just employing an operator in C++. And we should know that because operators can be overloaded, maybe it doesn't surprise us too much that the behavior that we view as a function call actually is a lot more flexible than it seems. Okay, that's getting a little bit too conceptual, so let's get back down to earth. You'll see that I've included the header functional, because we're going to need that for some of the types that we're going to be using over the next few videos. The standard library defines a whole ton of wonderful functional features. I'm actually going to go out of my way to not use those, although in the notes accompanying these, I've listed a bunch of them. Many of the functions I'm going to write to manipulate other functions in the next few videos are actually equivalent to standard library features. And as usual, of course, if you needed those in practice, you would use the standard library feature. The reason I'm not going to cover them directly is because it would sort of waste time. By the time we get there, you'd sort of know how to use them. And because I think it's really important that I write them in front of you to show you that there's no deep magic underneath them beyond things you could do yourself. And that the reason you should use a standard library is the convenience, not because it's mystifying. All right, so we're going to be working with a type called Std Function, which I guess shouldn't surprise us very much. For this video, all I have is some contrived stuff just to get us, I guess, to ease into that notation. So I've got a function that takes an int and prints it. I've got a function that takes a vector and computes the sum of the elements of the vector and returns it. I've got a function that takes the elements of a vector and multiplies them all together and then returns it. I'm not even bothering with things like constant references right now. I'm trying to strip things down to make the notation I have to use as easy as possible. And then I have some tasks to perform. Ooh, that looks pretty ugly. Okay, and so I've got some tasks I want to perform here. We're going to start with task number 1. So the goal of the video is to show that I am able to treat functions as data. And I'm going to start by proving that I can assign a function to a variable, which will also allow us to discuss what exactly is the type of a function when I assign it to a variable. So I'll start by compiling this. It's going to complain to me that on line 50, there is no such thing as SF. So what I want to do here is, in task 1, I want to make a variable called SF. And I guess I could use auto for this. I guess we could try it out with auto. It says create a variable SF, which refers to the sum vector function. Okay, well, let's just try it. I mean, if I want to make a variable, I'm going to use, I guess I shouldn't use the C-style initialization here. I could just say, let's just assign my sum vector function, so that's this function up here, let's just assign that to some variable and see what happens. As usual, we can learn a lot by experimentation. And we try it, oh yeah, and it works. Great. And so here on lines 42, 43, and 44, I'm calling print int on every element of the vector just to prove that print int works. And then I, down here, create a variable called SF, which is assigned the value sum vector, which is a function. And then I call that to prove that my variable SF is a function that I can call. And the sum is 33. And I've said before that that is definitely the sum of 6, 10, and 17. Okay, great. Well, I guess I proved my point then. So a function is data. Great. Okay, but wait, what's the type of SF? I mean, we care about that, don't we? Auto isn't a type. What is the type of SF? And the answer is, for our purposes, we should use this type for functions. And you'll note the strange legalese I just used there. The real type of SF is going to be something cryptic, but we're able to assign some vector to variables of the following type. Std function, and then in the angle brackets, I have to describe the function. So what is some vector really? I'm going to take the function signature for some vector and just bring it down so we can look at it. All right, so some vector, the sum vector function has this signature. And how do we define that? Well, we don't really care about its name. Just like how when we work with any other variable, the variable doesn't even know its own name. The variable has its own conception of what it is, but it doesn't really know its own name. We should instead try to describe this function based on what it does. Well, let's see. It takes as its only argument a vector of int, or a reference to a vector of int, and it returns an int. Really, if I had to describe that function from the outside, all I would care about is it takes a reference to a vector of int and it returns an int. When I want to assign the function to a variable, that's all I care about. And so what I do is I write this condensed version of the function signature. I write the return type, and then in round brackets, I write the types of all of the arguments in a row. I don't even bother giving them names. I just include the types, because the outside user of the function couldn't care less what the names of the arguments are. All it cares about are what arguments should it pass in. What the function chooses to call those things isn't really anybody else's business. Okay, so I can make a variable called SF, whose type is std function, and the function takes a vector of int, a reference to a vector of int, and returns an int. Notice the peculiar angle brackets with something in round brackets inside of them. That's a little bit clunky. We'll notice over the next few videos that it's actually something we can live with. Okay, so if I want a variable that refers to a function, I can use auto, but for our purposes, it's good to know what the type is, and we use this notation to refer to a function's type. Std function, and then the condensed signature of the function inside the angle bracket. So we'll try compiling that. All right, and there we go. It still works. Let's see what happens if I try the same with task 2. I would like a variable called p that refers to the printInt function. So just like before, I'm going to go up and borrow the signature to printInt so I can take a look at it. There it is. Okay, and I'm allowed to say, I would be allowed to write something like auto p here, obviously, just like we saw above. I would be allowed to write auto p as the printInt function, and you can do this. For the sake of the video, so we know the notation, let's write the type out in full. The reason we care so much about these types is because eventually we're going to want to accept them as function parameters, and therefore we have to be able to write them out. So let's see. PrintInt is a function, looking at its signature, that takes an int and returns void. So I would write it as, I would condense the signature into this. I remove all names and keep whatever's left over. So I delete the name of the parameter, I delete the name of the function, and I get void bracket int. And that is what I put inside the std function angle brackets. That's the parameter type for the std function template. All right, so we'll try that. I guess I'll delete this in the meantime. And we can see we are again calling the printInt function on all three of the elements of the vector, just like we expect. We iterate through the vector and then call that function. Okay, so I now have a way of referring to functions with this type notation. So now that a function object has a type, I can pass it around my program. I can make copies of it. I can pass it into functions. I can make a vector of functions if I wanted to. I should add, though, that the type of the variable p is this entire thing. So if I wanted to assign something to p, it would have to be a function that takes an int and returns void. And that shouldn't surprise us too much. Obviously, just like a vector of int and a vector of float are two separate things. All right, what's task 3? Well, task 3 is to implement a function called getOperation. And we'll go up and see the more detailed prompt up above. All right, task number 3. Write a function called getOperation that takes a string. Okay, I follow so far, so it's going to take a string. We'll call it s. And then it returns a function. Ooh, it returns a function. But we can do that. Functions are data just like anything else. It's either going to return the sum vector function, okay, that's a typo, or the mul vector function. Notice that both sum vector and mul vector have exactly the same argument type and return type. And so I'm actually going to copy that. Oh, actually, what I'll do is go down below. Here is the condensed signature for my sum vector function. So if I want to assign it to a function object, it would be std function of this stuff. So I want my getOperator function to return a function of that form. It's going to return a function. The function it returns will take a vector by reference and return an int. And both sum vector and mul vector meet that criteria. Okay, so what is the prompt? The prompt says, if the string you gave me is the string sum, then I'm going to return the sum vector function. And we know already that some vector can be assigned to something of this type. So this return should work. And then I'm going to cheat a little bit. I know the prompt says if it's the word multiply. Well, maybe I should be careful. Okay, so otherwise if s is the word multiply, then I return the multiply vector function. Okay, and then what happens otherwise? I guess I'll just throw an exception. If I'm only supposed to return sum or multiply and you pass in something that isn't either of those, then that's your problem. So I'll say invalid operation. So the idea behind this function is it's called get operation. Get operation. I pass in a string describing what I want, either sum or multiply, and it then returns me a function that can do that for me, that takes a vector and adds it up, or it takes a vector and multiplies together the elements. It's a bit contrived, but I'm hoping that I'm proving the point, that I can treat functions just like data. I can return them from other functions if I want to. So we'll go down here and test that out. Okay, this is saying, go get me an operation to do multiplication. So call get operation, I give it the string multiply. It returns a function, and then I call that function and I pass in my vector. So we'll see what happens if I call that. All right, and in this case, the product is 1020, and you can verify to yourself on the side that that actually is the correct product of 6, 10, and 17. I could also see what happens if I put in sum, and you can see here the product is 33. Well, this is not the product, it's the sum. I should actually be a little bit less sloppy. Let's try making two operations. We'll call this one add operation, and here it prints out sum, and then here I call get operation with sum as the argument. Okay, this video might be watched by more than one person, so I suppose I have some reason to be a little bit more fastidious. There we go. So the product is 1020 and the sum is 33. And so what I'm able to do here is write a function that returns a function. And that means I can treat functions as data using this std function type as a surrogate for the type of the function itself. And we'll see in the next video that that goes a long way to allowing us to decouple the behaviors of our programs by splitting everything up into smaller functions and then passing those functions around the program as needed.